Hi, this is Josh Mazure, and I'm presenting Artificial Intelligence Image Object Classification and Detection using DALL-E-generated images. So we'll start with the outline of what we'll cover today. First, we'll jump into the introduction of the project, then cover a literature review, go through the evaluation of the data set used for training, implementation of the entire project, then cover results, discussion, conclusions, and then references. So to introduce the project, it's quite common to have applications where the systems lack training or tuning images that you generally know are going to exist within a particular use case. So this poor model performance due to that fact is expected and normal to the startup of a project, in part and process variation is just going to be captured in time, or you assume it will be captured in time. So during this process, you're going to have a lot of false positives and false negatives. So really the question is, how do you fix this? Do you process, or does the process need to be rushed to provide particular parts or images for the machine vision system, or do you need to intentionally scrap or damage parts or manipulate them to create the images that you need? And really, how many of these images do you need to generate, and therefore, what's the cost of scrapping or manipulating all these parts? That can start to add up. Or the point of this project, can we use generative tools like DALL-E to generate images instead? So first, we'll cover a literature review of related projects. So plenty of augmentation algorithms exist using traditional programming. They can be model-based. These image alterations, they can be lighting, geometric, and they are known to improve models. There's also an example for synthetic aperture radar image classification using generative AI, but their results were inconclusive regarding the impact of generated images. Those images are also small and very specific with the context that they're seeing. On top of that, object change or movement detection, UAV images, was studied. They used generated images via a game engine, and they found that the model using these generated images show better results in supervised models. And then in industrial quality assessment, which is close to the purpose or related to this project, a classifier system trained with images formed in CAD was found to be on par with an original system that did not contain any generated images. So overall, using DALL-E generated images for model training is a novel task. I haven't seen other projects that are using a tool like DALL-E or another related tool. And on top of that, some of these other studies seem to suggest that the addition of synthetic image addition is helpful for a model. So next we'll jump into the data sets. First, the flower classification data set. So for testing, the original data set is composed of daisies, dandelions, roses, sunflowers, and tulips, and this was downloaded from Kaggle. These images vary in size, but they're all color JPEG images. The data set was quite large from Kaggle, but this was pruned down to 200 images for each class because a lot of images just simply had very little focus on the flower, so there weren't a whole lot of features to extract regarding the flower in the image. And so what was done, from that, there's approximately 1,000 total images. And to evaluate scenarios that I was covering earlier, in which it's a startup of a project, you don't have a whole lot of reference images for training. The training was split with 49, or the data set was split with 49 training images, 19 validation images, and 905 test images. and all of those are split evenly between the flower classes. After creating more training images via DALL-E, this added 70 images to the trained data set, and those were all split evenly between the classes. And DALL-E generation of images will be covered in a future slide. In here, just providing an example from each class from the original Kaggle data set. So on the left you have daisy, middle upper there's a pink colored rose, sunflower beneath that, tulip to the right, and then a dandelion to the far right. So it's already said, there are different features amongst the flowers, but there are some definite commonalities as far as potential color or the color of the background as well. And here are some of the DALL-E generated images for each flower type. On the left, we have a daisy moving to a dandelion, and then a rose in the middle, a tulip to the right of that, and a sunflower on the far right. Some of the images that would come back would have a plain background, some would have more of a forest setting, but generally the images did pretty well at recreating particular features of that flower type. So next we'll cover the data set for detection and detection of a stop sign. So the images are all 512 by 512 color images that were downloaded from Google Street View. The training data set is composed of 51 images containing a stop sign and 22 images that are null or void of a stop sign. The validation data set contains 13 images with stop signs, 11 without. The test data set is composed of 50 images with a stop sign and 50 images without a stop sign. So here again, a reminder, another example, the training data set is kept low to simulate the situation in which we are lacking examples. After DALL-E generation, 40 images were added with a stop sign to the training data set. And here we have a quick example of the original data set images. On the left is an example in which you can see a stop sign presented within the image. On the right's an image without a stop sign, but you can see features like the car's tail light that would provide a challenge where you have red, somewhat, of a hexagonal shape, maybe not on the far right side, and some white information or pixels in the middle as well. So definitely challenges within the data set for detection and potential false positives. And here are some of the images provided by DALL-E. And yet again, the implementation will be covered coming up. The left image provides a pretty good example where DALL-E did a good job of creating a stop sign. There's even a post beneath it, at a reasonable height as well, given the field of view. On the other hand, on the right, this is an image where simply that stop sign, size, location makes no sense given the context. So definitely some pruning that's required in the process, and that'll be covered later during the discussion and the implementation of DALL-E image generation. So now to cover the implementation. So in order to create the detection images from DALL-E, so a raw Google Street image would be uploaded along with a mask PNG that has an alpha mask and a prompt, and that would be passed to DALL-E 2, and that would return the DALL-E generated image. So in order to create that alpha mask PNG, two scripts were built. One would randomly place a mask within an image. Now there were reasonable limits as far as the maximum and minimum size, because DALL-E would return some pretty poor results if the mask was very small. And in addition, it just didn't make sense within the Street View's field of view to have a massive a massive stop sign. There was also a script that would return, or you could pass an exact location, but doing so, for every single image would take quite a bit of effort to generate those images. Compared to that, flower image generation only required a prompt for formation, and this could be passed to DALL-E 3. Both datasets use a prompt array with a random selection to add variation to the image request. So both programs had a big array. The flower array would insert the requested flower type into the array as well, and then randomly one of those prompts was selected with request to DALL-E for the image. After that, all labeling was completed in RoboFlow. This helped for image formation or image folder structure formation and importation of those images into Google Colab. And Colab was used for GPU access during training and inference. So next we'll cover the results of flower classification during training. We have the confusion matrix for the AI added model and on the left, and the original is on the right. You can see there's quite the improvement as far as misclassifications within the training data while using AI generated images. You go from 3 total that are misclassified compared to the original, in which there are 7. So continuing to look at the flower classification, the AI image add model on the left during 50 epochs of training reached a higher accuracy, and the test data set inference results, the accuracy for the dandelion, the rose, and the sunflower all increased with a minimal decrease in tulip accuracy. If you look at the model or the original model, the 50 epoch training reaches sub 70%, and you can see those accuracies that we just compared the AI dataset accuracy to as well. Now looking at the results of the stop sign detection models on the AI image add model, the confusion matrix shows that we're now actually picking up a false positive within the training data set compared to none within the original model. And then overall our accuracy by adding AI images decreases from 92% to 87%. Now we'll jump into a bit of a discussion of those results. So the flower classification performance improvement was notable in those several flower classes when using AI generated images. This was seen both in the test data set and training results. Now looking at the images, some of these results make sense where the images were high quality for reproduction of features, actually showing features that are useful to be able to classify those images. And obviously too, the stop sign detection performance declined when using AI generated images, and that was completely due to false positive detection rate. There were no examples in which a detection was missed of an actual stop sign. So within that, random bright objects began to be detected rather than objects actually resembling a stop sign. So that's using the AI image model that began to be a problem. And as mentioned, all stop signs were still detected though, but we are now picking up on extra red features within the image. So overall, to continue the discussion, we saw some successes with classification and some issues with detection using AI images. In the future, evaluations on larger data sets and subsets of those data sets in combination would be insightful as far as at what point does the impact of adding these become a problem if you have a lot of images already. Definitely some some good news seeing the improvement in classification. So there is some hope there that this could be used in future apps, even those with larger data sets, but knowing its impact would be very helpful. Also, evaluating the addition of these images on additional data sets would help understand if it's a detection or classification specific, improvement or deterioration, or if it's just specific image context, like, Google Street View compared to flowers. Also, the inclusion of segmentation model parameterization, given more human resources for labeling and compute resources for parameterization. There was no, major effort here other than holding parameters constant across a classification and detection to detection model. Those were held the same, and then the training began. Also, an improvement in prompt and inclusion of prompt engineering study with image quality analysis. Really, that array was set up, and then images were requested, but there was no further evaluation from there. Additionally, the DALL-E 3 model, you can't mask a photo anymore. So that would be an improvement to use newer models with the masking. And any future iterations of DALL-E or alternatives that provide better photorealism or image quality would also be very helpful. So these are all considerations that, hey, if these were released in the future, if they were available, that reevaluating be a very valid thing to look at. So to conclude the project, we performed analysis on data sets with limited training data to simulate scenarios found commonly within machine vision, and we put detection and classification methods on those images, or on those limited data set images. The flower classification model, within that, adding AI generated images, improved model accuracy and test data set, and while training the model, and the Google Street View stop sign detection model, the addition of these images led to false positive detections, and probably noise within the data set, and therefore decreased the model accuracy. Here's a list of references for the project. Thank you for your time and attention.